a ring containing K, which was the adeles. So that was this restricted product over all the places of the completions where you insist that in almost all places for any given adele, it's integral. So this is the restricted product over what we call the agent. And that's a ring containing K, because any given element is integral in almost all places. And we showed that the non-vanishing of the discriminant was equivalent to the K in denses. It's a locally compact ring, and this is a discrete subring, and the quotient is compact. So a good setting for Fourier analysis, also for Pointryagin duality, etc. And then last time we also studied the units in that ring, which are called the edels, which are the restricted product over V of the KV of the non-zero elements with respect to the non-zero, to the units locally. And we saw that this was a locally compact group that contained the multiplicative group of K, and that there was a canonical character of it, the norm character, for the positive real numbers, where the norm of an edel is given by the product over all V of the local norm of the edels. And in this product, almost all terms are equal to 1. And we saw that this subgroup was in the kernel of the norm map. And we called the kernel of the norm map A star 1, kernel of the norm map, which is a surjective map, because at the real place you can put anything, and the absolute value on the real numbers is surjective to the positive real numbers. So we had a subgroup, which was the kernel of the norm, that contained K star and the big theorem, which is equivalent to all the theorems on finiteness of class group, finite generation of the unit group, is that this is discrete and co-compact. And I began the study of the characters of this group, and so we want to study the continuous homomorphisms psi from this compact group to the circle. Those are the continuous characters, and also we want to study continuous homomorphisms chi from the edel classes, not to the circle because that isn't a compact group, but to the multiplicative group of complex numbers. And an example is chi is equal to the norm map. That's a homomorphism which is continuous to the positive real numbers, and you have a lot of characters of the positive real number, so you can take this to the S power for any complex number. That gives an example of continuous homomorphisms of the edel class group. Okay, so last time I constructed for you, and also noted that when the number field was the rational numbers, we saw that the edels contained, of course, Q star, and it was a product of Q star with a certain subgroup, namely, you took the positive real numbers, and over all primes P, you took the p-adic integers. And that was equivalent to the fact that the class number was 1, and that the unit group was plus or minus 1. Z star was plus or minus 1. So you got a very simple decomposition of the edels, and in particular, a character of the edel classes, A star mod Q star, is just a character of this group, continuous character of this group. And the continuous characters of this group you get by taking a character of the positive reals, that's just given by a complex number. And this is a compact group, so a continuous character to the complex numbers has finite order. So the continuous characters, this group is the inverse limit over all n of Z mod NZ star for a finite group. So continuous character of A star mod Q star has the form norm to the S times a chi0, where this is a character of Z mod FC star. And from this, we could make an L function. And I'm going to show you that for each continuous homomorphism of the Edel classes, you get an L function. And these are the L functions that Heck has studied in a much more classical view as characters of certain ideal groups. Okay, and then the L function I is, in this definition, is going to be the L function of this Dirichlet character evaluated at the complex point S. Okay, so I have to tell you how you define the L function of a character of the Edel classes. Okay, now it turns out that such a homomorphism is made out of local homomorphisms, just like this one is. This is, you know, some character of A, which is given by the Edelic norm, and that's a product of local norms. Okay, so it turns out that every character of the Edels is made out of local characters. If chi is a character of A star, forget about the fact that it's trivial on K star. Forget about that. Then inside of the Edels, by a character, I just mean a homomorphism to C star. I'm not going to keep, Tate calls these things quasi-characters, meaning that you don't insist that it have absolute value 1. Then inside of A star, I have the multiplicative group of every localization, because you just take the Edel, so you have an AV here, you map it to the Edel, which is 1 everywhere except at the place V, and you put an AV. So this is a subgroup of the Edels for all places V. And so I can take this quasi-character and restrict it to KV, and I get a homomorphism from KV star, right? So a restriction of chi to KV, which I'll maybe could just call chi V, is a homomorphism from KV star to C star. And those restrictions aren't arbitrary. You can't get an arbitrary sequence of characters. But if I have, on the other hand, given a collection of characters, chi V of KV star for all V, with the property that chi V, when restricted to AV star, is equal to 1 for almost all V. Namely, that's what we called an unramified character. Remember that in this local field situation, let's go back to the local fields over here, we had the units inside of KV star for V finite. It doesn't make sense of the infinite places. And these were the elements where the absolute value of alpha V was equal to 1. So not just integral, not just less than or equal to 1, but equal to 1. So its inverse also had absolute value less than or equal to 1. And the quotient, so these are also the elements alpha, such that the ORD V of alpha is equal to 0. And you have a homomorphism from KV star to Z, which takes alpha to this is the ordinal homomorphism. And that's surjective because we showed that there was an element in AV of valuation 1, so takes pi to 1, so it's surjective homomorphism, and the kernel is precisely this. So if we have a continuous homomorphism of KV star, which is trivial when restricted to this unit subgroup, it's a quasi-character of Z. And quasi-character of Z is determined by what it does to the element 1, right? So if chi V of KV star is unramified, and that just means trivial on AV star, it is completely determined chi v of pi v, which is just a non-zero complex number. And that non-zero complex number can be specified arbitrarily, because we know the quasi-characters of Z. You just send pi v to any complex number you want, which is non-zero, and then you insist that you extend that to a character of this by insisting that it's trivial here. And since every element in here can be written as a power of pi times a unit, if it's trivial here, and we know it on pi, we know it on all of this. So those are the unramified characters. They're just indexed by non-zero complex numbers. Okay, now I claim that suppose you're given a collection of characters, one for each local field, and at almost all the finite primes, that's the only time you can talk about it, it's an unramified character. Then you can make a character of the edels. Then chi, which is the product of the chi v's, is a character of A star. Because, for the same reason that I could do this with the norms, namely, if I try to take this character on any given edel, at almost all finite primes, that edel is a unit. Consequently, the local character is trivial. And consequently, the product of chi v of AV is a finite product. And so you can evaluate it, and we'll call this chi of A. Okay? So, and conversely, it's not difficult to show that any character of the edels, which gives a finite collection of characters, has the property that for almost all V, these characters are unramified. And so that's exactly what the character theory of the edels is. It's just giving a collection of local characters, almost all of which are unramified. In this case, all of the finite primes are unramified, because the norm, when restricted to the unit group, is trivial. But you could have characters here which are trivial on all of these except for a finite number, namely the primes dividing your fixed f, right? And you still get an edel class character. Okay, now notice how open that is and how useless it is to study characters of the edels. There are too many of them, because all it is it's saying, well, look, I'll give you an example of a character. For almost all finite primes, I just choose a complex number, right? And for all other places, I take the trivial character. That's a character of the edels, right? It's too much. It's just too much. But if you say it's a character of the edel classes, namely if it's trivial on the subgroup K star, then there have to be some subtle relations among these complex numbers that you've chosen so that it actually is trivial on this diagonally embedded subgroup. And that's what makes it so interesting. So for any character of the edels, I can define an L function. Or any, I'll write it chi is equal to the product of chi v of A star, we can formally define an L function. But I insist on the word formally, namely it's defined, L of chi is by definition the product over the finite V where chi v is unramified. So that's an infinite product, right? Because there are infinitely many such places. 1 minus chi v of pi v inverse. This is a complex number. It's a non-zero complex number. I take 1 minus it, I invert it, it's another complex number, and I take the product of those. The problem is, there's no reason that that product should converge. No reason at all. And consequently, that's the emphasis on formality. Okay, but what we're going to show is that if this character is trivial on K star, this not only converges, but extends to a meromorphic function on the plane. And I'll show you what I mean by that. Okay, let's see what this is, by the way, for our character. So let's try this for the Edel class character chi is norm to the s. All right? What is chi v of pi v in that case? Well, it's the local norm of pi v raised to the s power. The local norm of pi v, remember, was you took the number of elements in the residue field to the minus ordinal. So that's qv to the minus s power. Correct? The norm of pi v is q inverse. Okay, so this L of chi is the product over all finite places v, because all finite places are unramified for this norm character, of 1 minus, let's write it, the norm of p sub v to the minus s inverse, right? So that was the Euler product that defined the zeta function of our number field. And this converges for real part of s greater than 1 by comparing to the Riemann zeta. Okay? So in that sense, this formal product made sense. How about when k is equal to q and chi is chi naught times the norm to the s? Because those are the Edel class characters there. Okay, so this is unramified at p if p does not divide f, the character the conductor of this Dirichlet character. And then L of chi is the product for p not dividing f of 1 minus chi 0 of p to the minus s inverse, because the value of the Dirichlet character on the uniformizer is just that. And this is exactly what we call L chi 0 of s. And that converged also for a real part of s greater than 1. In fact, it converged if chi was non-trivial for a real part of s bigger than 0. Okay? So, so that's going to be, okay. So, the theorem that Tate is going to prove, which is in some sense a modern version of Hecke's theorem, is that if chi is a character of A star, which is trivial on K star, then, well, I'm going to write it in a funny way. I'll do better. All right, then then the product defining L chi times norm to the s. So I can always take a character and multiply it by a power of the norm character and get another Edel class character. And that would mean instead of having this, L of chi times norm to the s would be the same product, but I'd have 1 minus chi v of pi v times qv to the minus s power inverse, right? So if I take s larger and larger as a real number, this complex number becomes smaller and smaller. I mean, qv is bigger than 1. So the product defining converges for real part of s large enough and has a meromorphic continuation to all S in C, usually without poles, and they have a functional equation relating L chi times norm to the S to L chi inverse times norm to the 1 minus S power. Of course, in the functional equation, this product over the finite v is not enough. You have to add some factors at the infinite primes, which we'll see. So you need factors like this gamma bar of S and gamma C of S for functional equation of the zeta function. So it's not quite this simple, but you have to, there are other factors you have to put in this thing for the infinite v. But you don't have to put any other factors in for the finite v where the character is ramified. Okay, let me give you a better way of stating this so you don't have to do this real S greater than equal to 0. We're going to associate a real number to any character of the E-del classic. So notice what this is saying. Even the saying about the convergence says something about the size of these numbers, of these complex numbers, for a character trivial on the on K star. They're not arbitrary complex numbers. They're all woven together by the fact that they have to be trivial on K star. So that's the convergence. And then the functional equation is another way of saying that they're not arbitrary numbers. Because I could make them of a fixed absolute value, and this would converge, but it wouldn't satisfy functional equation. So it's an even stronger statement. Okay, so now Kay got a very clever idea of defining the real part of a Hecke character. So these characters, so from now on I'll call the characters of A star, which are trivial on K star, I'll call them Hecke characters. In homage to Hecke, who never studied E-dels or A-dels or anything like that. Okay, so Tate defined definition, chi a Hecke character. We're going to define a number called the real part of chi, which is going to be a real number. And you might expect that the real part of the norm to the S character is going to be the real part of the complex number S. Okay? So it's going to generalize taking the real part of a complex number. So the way we do this is we have this character chi from A star mod K star to C star. And then we take the homomorphisms from C star to R star plus given by the usual absolute value. And we call that, and we can take the composite of these two things, and we'll call that the absolute value of chi. Where first you apply chi, and then you apply the absolute value on the complex numbers to the values of things. Okay? So this character on an E-del is the absolute value of chi of the E-del. Okay. Now, this is a homomorphism, continuous homomorphism to a group which, unlike C star, has no non-trivial compact subgroups. Right? I mean, this is isomorphic to the additive group of the real line under the logarithm. So there are no compact subgroups other than the identity. And so if I restrict chi, so the absolute value of chi must be trivial on the compact quotient A star 1 mod K star, because we showed that this group was co-compacted here. And so the image of this subgroup would be a compact subgroup of this, which is 0, which is 1. So the absolute value of chi factors through A star mod K star, and then that maps via the norm to the positive reals. That's the quotient, let's call this A1 star, which is isomorphic to the positive reals. It factors, so it gives a homomorphism from the positive reals to the positive reals. And all homomorphisms from the positive reals to the positive reals are just given by taking t to t to the s power. Sorry, t to the sigma power, where sigma is a real number. Okay? And so that defines the real part of chi, sigma. And when you take the absolute value, you view it as a character of this quotient group, which is canonically isomorphic to the real numbers by the absolute value of d del. So in other words, chi is equal to absolute value of chi of A is equal to the norm of A to the sigma power, where sigma is a real number. And that's the real part of chi. Okay? And if you do it for this, the real part of this, well, this is a complex number, and then you take its absolute value, and the absolute value of this is the absolute value to the sigma power, where sigma is the real part. So that's the real part of it. Okay, and if we multiply, in fact, the real part of chi times norm to the s is equal to the real part of chi plus the real part of chi to the s plus this sigma. When you multiply characters, you add the real parts. That's true for any two characters. I mean, you just figure it out because you're multiplying these characters here, so you're adding the exponent. Okay, so let's restate the theorem of Hecke and Tate in a nice way. So now we don't have to multiply by chi. So Hecke, Tate. The product defining L chi converges if the real part of chi, it turns out, it converges if it's large enough, and it turns out it's enough that the real part of chi is greater than 1, has a meromorphic continuation to all chi. So you get a structure of a Riemann surface for all the Hecke characters, because the local neighborhood of chi is given by multiples of the norm characters. So you get a little parameter in the neighborhood of chi where the local, the things close to it, or things of the fine, it extends to all chi. So you get a meromorphic continuation to all chi with a functional equation relating L of chi, which we can now evaluate, well, except for certain characters, to L of chi inverse times the norm. Because again, this has all the S's stuff in it. And it's actually holomorphic for chi not equal to the trivial character and the norm character. That's like the zeta function at 1 and the zeta function at 0. Okay. Okay, now, I'm not going to prove this. This is exactly what's proved in Tate's thesis. Of course, the functional equation, you have to multiply by L infinity of chi. There's a certain factor at the places dividing infinity, and then you have here L infinity of chi inverse times the norm, and then there's some factors in the functional equation like there was in the zeta function involving the discriminant and the conductor of the character, but we're going to leave that. What I wanted to finish by showing you is the relationship between characters of the EDEL classes, this very nice formulation where you give yourself a local character for all primes V with this property, and which is trivial on K star, and characters of the ideals, which is how we started this out. So it's always good to see the relationship between the modern version of a theorem and the classical version of a theorem. So we're going to show that characters of A star mod K star are related to certain characters of IF, the ideals of K prime to F, with specified behavior on PF. The principal ideals with a positive generator congruent to 1 mod F. Okay, so that's how Hecke worked, and this is the Tate reformulation. And it turned out that this was more flexible because, as I say, you have a chi decomposed into a chi V, and what Tate did was to prove this functional equation. He proved functional equations for these local L functions at chi V. So you could define the local L function of chi V as just 1 minus chi V pi V inverse, or you could have something at infinity. And Tate proved things about these local L functions and put them together into the functional equation. Okay, so let's do this translation between a character of E-del classes and a character of ideals. Well, certainly a character of the E-del classes gives 1 of IF, all right? So, so start with a chi of A star, in fact, just a character of A star. Okay, so that's given by a product of local characters. And we're just going to look at the finite parts of them for the moment. So for almost all V, have the complex number chi V of chi V. For finitely many V, the local character, when restricted to the units, is non-trivial. Why don't we do that? Why do we do that? Well, we can't get a complex number out of it, but we go over to our local board and see if we have any information. And in fact, we have a filtration of K star. Well, it contains the subgroup of units, and there the quotient we saw was Z. But then we saw the units contained the units that were congruent to 1 mod pi V. And here the quotient is the residue field, which is a finite, the multiplicative group of a finite field, which is cyclic. And then we have the units which are congruent to 1 mod pi V squared. And here the quotient is the additive group of the residue field. And this continues, where all the subsequent quotients are the additive group of the residue field. And this is a descending filtration, and the intersection of all of these is the trivial group, because if it's arbitrarily congruent to 1, it's 1. And so if you have a continuous character, it's going to be trivial on one of these subgroups. And the first one determines an integer, which is called the conductor of the character. So if chi V is not equal to 1 on A V star, then it's equal to 1 on some 1 plus pi V to the FV AV. And the first one is called the conductor of the character. So that's a local invariant that tells you, in some sense, how ramified. So if you have a character, for example, if you have a character chi V of ZP star, which is non-trivial, and you do the filtration, 1 plus P ZP, 1 plus P squared, ZP, etc., then the conductor, if it has conductor F, if a character of the quotient Z mod P to the F Z star. Okay, so the finitely many V, which are this, gives us a conductor FV, an integer. Okay, and we make an ideal which is associated to this original character of the Edels, by using that local information, we could define the conductor of chi to be equal to the product of these ramified primes to the FB power. And that gives an integral ideal of the ring of integers. Okay? So it just encodes the primes where the character is ramified, they're finitely many, and it tells you at each one of those primes how ramified it is, namely how deep in this filtration you have to go before the conductor becomes trivial. And for the Edels of the rational numbers, that has to do with sort of what level you're at for a Dirichlet character. Okay. Now I'm going to define now a character of the ideals that are prime to F. Define from chi and its conductor F, which is an ideal of the ring of integers, a homomorphism phi from the ideals prime to F to C star. This sort of thing Haeckel worked on. Okay? Well, an ideal which is prime to F can be written as, so J is the product of Qi to the Mi power, where these are prime ideals, which are not the prime ideals in the conductor, so they're relatively prime to F. Relatively prime F. And the mi's are integers. I mean, these are fractional ideals, so these are integers. And I map that to the product over I, chi, the local component of chi at the place associated to Qi of pi to the Mi power. So for every ideal which is relatively prime to F, the character is unramified. I can evaluate it on the uniformizing parameter at Qi, and I get a complex number, and I take that to the Mi power. Okay? So this is using all of my terms in the L function, wherever they were, at unramified primes. And it's using a little information at the ramified primes, namely how deep I have to go in the filtration to get a trivial character. Okay, now the claim. So this works for any character of the Edels, because almost all the terms are unramified, so it gets me these numbers, which I use in this definition, and it gets me a conductor. Claim. If the global character is trivial on K star, so if it's a Hecke character, then it is completely determined by the values of by psi on IF. So this homomorphism on ideals prime to F determines the Hecke character completely. Why? And notice, by the way, that these values are all I need to define the L function of chi, because I just evaluate on a prime ideal relatively prime to F, and that gives me the term in the L function. Why is it true that a continuous character, if I know it on all the unramified primes and is trivial on K star, then it's determined? Well, because, why? First thing is that K star is dense in a finite product of KB star. So that's sometimes called weak approximation. I mean, it's clearly dense in one of them, and that you can do simultaneous approximation in a finite number of them is, I'm going to just assume that. That's an approximation theorem, an analogous, it's a generalization of the Chinese remainder theorem. This is sometimes called weak approximation. I'm going to leave that. So therefore, hence, the product K star product of V not in S of KV star, well, the restricted product, is dense in A star. Because, I mean, A star is just the restricted product over everything, and K star is dense in this finite product, and then you have the rest of it. Okay? On the other hand, psi, so now take S equal the union, well, the prime's dividing infinity, and the prime's dividing this conductor F. That's a finite set of primes. Okay? Then on this part of the dells, the character is determined by phi, because phi tells you what to do at any finite place which is not ramified. And on this part, it's trivial. And if this subgroup is dense and have a continuous character, and I know it on this subgroup, I extend it by continuity. Know it everywhere. So that shows that this part of the character that Hecke worked with is enough to determine the character on the dells. But you can't take any character here and turn it into a character which is trivial because there's some intersection in these subgroups. And so if you specify an arbitrary character here, it's not clear that its restriction to the intersection will be trivial. So let's see what that means. And then we'll start to see this subgroup coming into play. So it's determined by phi, but what extra properties does phi enjoy to come from a Hecke character chi? Because we saw we could make this for any character of the dells. It just needed it unramified almost everywhere. And but if we want to make it something out trivial on K star, it's quite restricted. So take a principal del, which such that the ideal generated by alpha is prime to F. Okay, then we know a couple of things. First of all, when we evaluate chi on alpha, it's 1, because it's a Hecke character. So trivial on all the principal field elements. On the other hand, this is equal to the product over all V of chi V of alpha V. Right? Okay, so let's write this in an intelligent way. At the primes, so this is the product over V in S, which is, again, S infinity union SF, which we don't know too much about, of chi V of alpha V. And then at the primes in S, we're just evaluating at some power of the uniformizing parameter, of a V unramified. Alpha V is some I V to the MV, and chi V of alpha V is just this unramified thing to the MV power. That's all we need to know. Well, it's this times some unit, but chi is trivial on the units. And so the product over all those V is just psi of the principal ideal generated by alpha. Right? We can evaluate this because this principal ideal is prime to F, has only primes in it, and for each prime that divides this principal ideal, I get this value. Okay. Good. So if we also insist, so this is alpha and k star where this ideal is prime to f. If alpha happens to be congruent to 1 mod f, so that the ideal is the principal ideal is in PF, well, what happens then? Well, what that means is that we're deep enough in the local filtration so that the local character is trivial on alpha. Then chi v of alpha v is equal to 1 for all primes v dividing f, because that's exactly how the conductor was defined, so that if you're congruent to 1 mod it, the character was trivial. And so that this product over the primes in dividing f is trivial, and we're just left with the product over the primes dividing infinity. Okay, so we conclude that the extra property is that if alpha is in k star, the ideal generated by alpha is prime to f, and alpha is congruent to 1 mod f, so that this ideal, so this ideal alpha is what we call PF. The principal ideal is generated by something congruent to 1 mod f. Then, taking this identity, we see that the product over v dividing infinity of chi v of alpha v has to be equal to phi of alpha inverse. So it says that this character on IF, oh, and what is this? What is this? Well, we know the continuous characters at the infinite places. So if v is real, this is just the sine of alpha v to the epsilon v times the norm of alpha v to some sv, because that's what a character does to a real number. And if it's complex, you have a little bit more freedom. You get alpha v over alpha v bar to the mv half integer times the norm of alpha v to the s power. So we know the continuous characters at the real and complex places, and it says that when you restrict phi to the principal ideals congruent to 1 mod f, then the value has to be determined by its location at the complex places given these kind of formulas. In particular, if these characters were trivial, if for example, we knew that this Hecke character had finite order, see, then this would have to be 0, and this would have to be 0, and that would have to be 0, and you could have a little sine character, but that's it, because those are the only characters of finite order of R star and C star, right? So if chi were finite order, this is basically just given by a collection of sines. And that would say that if you had an alpha which was congruent to 1 mod f and was also positive at all the real places, so its sign was trivial, then this product would be trivial, and this would have to be 1. So if chi is of finite order, which is certainly a very interesting case, as we're going to see, and alpha is also assumed positive in all the real places, then phi of this alpha has to be equal to 1. And that's where Hecke started. The characters of IF, which when restricted to PF plus, right, this means the ideal alpha is in PF plus, the characters of IF, when restricted to these subgroups, were trivial. He could prove a functional equation for those. Well, those are exactly Tate's Hecke characters which have finite order at the infinite places. But then Hecke discovered that he could prove the functional equation not assuming it was trivial at infinity, but it behaved like this at infinity. And those are just the local characters of the infinite places. So to translate back, if you have a character of the edels, then you get a character of the finite unramified primes. And that determines it completely because of this density statement. But that character is not obvious, is not arbitrary. It means that when you restrict it to the principal ideals which are sufficiently congruent to one modulo conductor, that is determined by its components at the infinite places of the element alpha. And in particular, if it's a finite order and the components at the infinite places are all positive, then that has to be trivial. Okay. So I'll give you some examples of a chi, which is not a finite order in this case, which are really quite interesting and will lead us, we'll come back to them when we get to elliptic curves. The characters of finite order turn out to be, by, and I'll do this next week, by class field theory, the characters of the maximal of the Galois group of the maximal abelian extension. Okay, so they're very interesting number theoretic objects, just the Hecke characters of finite order. But the characters of infinite order, which appeared to be bizarre in Hecke's work, but just turned out to be other characters of the Edel classes, turn out to be very interesting in the study of elliptic curves. So I'll give you an example or a couple of examples of that. So we can't do that if the field is the rational numbers, because the rational numbers only has real places, and the only interesting characters here are like the norm to the S character, and that's not so interesting. But if we have an imaginary quadratic field, let's do Q of I. Well, let's do an imaginary quadratic field. Let's make an interesting. So there are two nice things that happen here. The unit group is finite of order W, and in fact the order is either 2, 4, or 6. And these only occur in 2 cases. And the class group we know is finite. So I'm going to make a psi from all ideals the homomorphism to well, I'll just make a homomorphism to K star. We'll start with that, and then that won't be trivial on Edel classes or anything like that. But let's see what it is. And take an ideal, J, and raise it, let's say, finite of order H. Take your ideal and raise it to the H power. Okay, so that's generated by some beta. But beta is not unique, because you can multiply beta by any unit. But the units have finite order, a cyclic subgroup of order W. So if I map that to the element in K star beta to the Wth power, that's a unique element. So I assign to any ideal, J goes to beta to the W power. It's a homomorphism of ideals, because if I multiply 2 ideals, I multiply the generators of their H power, and then I multiply the W power of those generators, right? So that's a homomorphism where F is equal to 1. Okay? Now what happens when I restrict it to the principal ideals, which are, well, I don't have to do any congruences. Principal ideals. So if J were principal, gamma, it's just mapped to the, you take this thing and you raise it to the WH power, right? Which, if you think about it, depends only on the complex position of gamma. Namely, this is a homomorphism where the complex character, chi infinity of Z, would be Z to the minus WH power. That's a perfectly nice homomorphism from the complex numbers to itself. And if you see, you'd see that if I apply this to those principal ideals, I just get a product of chi infinity of some nice character. So that's an example of a Hecke character. And it clearly doesn't have finite order, because these things are not roots of unity. I mean, I'm really thinking of this K star inside of C star by one of the embeddings. Okay? So that's an example of one where the conductor is 1. Here's an example of one that I used in my thesis. In fact, it was my entire PhD thesis. So you can make your entire PhD thesis out of one heck of character. Quite amazing. So let's try this. Let's take k to be imaginary quadratic. Oh, so what does the L function look like? Sorry, what does the L function look like? Okay, well, let's take a look at it. We're going over. No, I have plenty of time. All right, so let's take the case where k is q of I. So there h is equal to 1 and w is equal to 4. All right? So chi of all the ideals are principal, so I have a plus bi. What is that equal to? It's equal to a plus bi to the 4th power. That's all it is. That's a well-defined complex number. Right? And so the L function, well, I'll put an S in it, why not? Is the product over all the primes. So let's say, yeah, over all the primes of these, you know, yeah. And when you assemble all the primes into all the numbers, you just get the sum. Well, it's 1/4 the sum, AB not equal to 0, 0. If I did this right, 1 over the quantity A plus BI to the 4th power. And these kind of series were studied by Gauss. So first you take the product over the primes, then you write it as a product over ideals. So this is an example of a Hecke L function, which if you multiply by norm, you know, if you multiply this times, you know, a squared plus b squared to the s power, which is the norm of the ideal, right? And then that has an analytic continuation and functional equation and everything like that. All right, so now I'm doing my thesis, and then we'll stop. Okay, so now take an imaginary quadratic field of prime discriminant. Where P is common to 3 mod 4. And for simplicity, P is bigger than 3, so W is equal to 2. That's why I assumed that. Okay, now it's known that, and we're going to see next lecture, that to an imaginary quadratic field, there's a canonical abelian extension called its Hilbert class field, which is an extension field where the Galois group is canonically isomorphic to the ideal class group. So if the class number is 1, it's k, and if the class number is bigger than 1, you get an extension. Okay, and it's also known, here we took the ideal and we raised it to the h power. Well, the generalization of that is if you take an ideal of the Hilbert class field and you norm it down to the imaginary quadratic field, that's always a principal ideal. That's a property of the Hilbert class field. The norms of all ideals are principal. Okay, so here's what I did. I said, take conductor, and that's why it's more interesting. Take conductor to the ideal square root of minus p. So we only have to define phi. We're going to define phi on the ideals of H, which are prime to P. Okay? So we take an ideal J. We norm it down to K, and we take a generator of it, but there are 2 generators because they're 2 roots of unity, right? Okay. But this ideal is prime to P. So we can consider beta modulo the ideal square root of minus P in this ring. Okay? And we have 2 generators, plus and minus beta. But P is congruent to 3 mod 4. So exactly one of these generators is a square, modulo the square root of minus P. Right? Because minus 1 is not a square, mod P. And the squares are sort of half the generators. This is an element in Z mod PZ star. And half the elements are quadratic residues, and half aren't. But if beta were a quadratic residue, minus beta isn't, and vice versa. So you take this to be the unique generator beta of the norm of J, which is a square modulo square root of minus p. And you can do that because your ideal is prime to p. You can't do that for the ideals dividing p. You can't say which generator you're taking. And that's a homomorphism from the ideals of H prime to F down to K star, and then I can embed K star into C star by one of its embeddings. And you'll see similarly that that's given by a very simple, you see H tensor R is C to the H. So there are H different places, and in each place you put chi infinity of Z to be Z inverse. Just that. Exactly that for all the H places. And then you see this beta is given by the product of the chi infinities. Because it's the norm. Okay, so that's a Hecke character. It's kind of nuts, but there it is. And the way I got a thesis out of this is it turns out that the L function of the associated Hecke character is the L function of a certain elliptic curve over a subfield of H, a quadratic. This is an extension actually of a subfield called Qj, elliptic curve over Q of J with complex multiplication. And then I used the fact that I knew everything about this Hecke character to study this elliptic curve. And the way I got this thesis was that Sayre called me into his office once in graduate school, and he showed me this Hecke character for p equals 7. So for p equals 7, the class number is 1. So you don't need the Hilbert class field or anything like that. You just take the ideal, and you take it to the unique generator, which is a square modulo 7. And he showed me this elliptic curve and everything, and isn't this wonderful? And he said to me, but this probably doesn't work in the general place when the class number is bigger than 1. It's an accident that the class number is bigger than 1. And since I wanted to show him, I did it in this case. So, in general, it's very good if you're talking to your advisor and your advisor says that this sort of thing can't be done. That's your chance. That just means when the senior mathematician tells you that such and such can't be done, the translation is, I can't do it. Okay? So have a good Thanksgiving, and I'll see you Tuesday when we get back, and we'll do a quick review of class field theory, and then on to elliptic curves.
Oh, and
there's an announcement. There's a talk.
On like Ilan's talk on Monday is before the next class, so we should announce it late. So
exactly. So there's a visitor coming who's a potential candidate in number theory, and her name is Ila Varma. She gives very nice talks. She's going to talk about her work in arithmetic statistics. She wrote a thesis with Manjul Bhargava, so if any of you are interested in that. And she'll be going to lunch on Monday, so people want to go. She wants to meet graduate students. Why anyone would want to meet graduate students is a mystery to me. I think the trick is to avoid graduate students, but Ila wants to meet graduate students, so if you want to come to lunch, get in touch with Alina, who'll be arranging the lunch and everything.
And also, if you're interested in the 205 next quarter, this is perfect. She's going to explain exactly
why you should take 205. I need proposals for, okay?